This session recapitulates materials on collections seen in the previous sessions in the context of a larger example. The task will be to design a program that converts telephone numbers to sentences.
So here's the task. You know that phone keys have mnemonics assigned to them. If you look at your smartphone or another phone, then you find that 2 gets associated with ABC, 3 with DEF, 4 with GHI, and so on. Assume you're giving a dictionary, which is a list of words that we call words for simplicity. What I want you to do is design a method translate, such that translate of a phone number would produce all phrases of words that can save as mnemonics for the phone number. So it's something like 1-800-CALL-ME, only for the words in the dictionary. So here's an example. The phone number that is given by the digit string 722524736 should have the mnemonic Scala is fun as one element of the set of solution phrases. Why? Because the digit 7 has as one of the letters associated with it the S. 2 has both C and A, so that gives SCA. The 5 has the L, so that this gives SCAL, and so on. So you see the principle. That's actually an example that has been studied before. I've taken it from a paper by Lutz Brecholt. Paper is called An Empirical Comparison of 7 Programming Languages. It appeared at IEEE Computer number 33 in 2000. At the time, the students were asked to solve this puzzle in a set of scripting languages and in a set of general purpose languages, and then various measures were produced, like how long it took them, how many bugs, how long the program was, how fast the program was, and so on. One fairly obvious outcome was that the scripting languages were shorter, about 100 lines of code for the solution, compared to 200 or 300 lines of code for the general purpose languages. There were a lot of other interesting findings in that paper, so if you come across it, I encourage you to read it. So let's see how we would solve this problem in Scala using a worksheet. I've already laid down some intermediate steps for you towards the final solution. The first thing we want to do is get a dictionary of useful words. We have put up one for you under the LAMP EPFL-CH site, so here you find the full URL. So that using that URL, we can use the source object that we have imported from Scala.io to get an iterator that can read in one by one all the characters in that under that URL. And the first thing we are going to do with that is we are going to call getLines, and that would now give you an iterator that gives you back the strings that make up the individual words one by one, because in the dictionary, in fact, every word is in its own line. Good. The next thing we have given is the mnemonics map, which is the same on every phone here. So it's just a map from character to string that contains the associations that you know. So the first task to do then would be we need to invert the mnemonics map. So now we wouldn't have a mapping from digit to character strings. We want to have a mapping from characters to digit. Call that map carcode. So the question is, how do we implement that map? Well, one thing we could do, of course, is write it down. We could say A maps to 2, B maps to 2, and so on, for every letter in the alphabet. But that's a bit repetitive, and it violates the so-called dry principle. Dry means don't repeat yourself, because in a sense we have encoded the same information from this map twice. So in the unlikely case that the mnemonics bindings for phone would change some points in the future, we'd have to change 2 places in our program to reflect that, instead of ideally just 1. So let's do something that's shorter. So what we want to do is we want to, in a sense, invert this map, now going from a map from the characters in the string here to the digits. So the way we can do that is with a for expression. So we let the for range over all the key value bindings in the map. So the key would be a digit, the value would be a string, and it comes from the map here. And then we still need to let the second generator range over all the possible letters in the string. So we say letter taken from string, and we yield. What do we yield in that case? Well, we yield the binding that goes from the letter to the digit. And what you see here is now a map that indeed inverts the mnemonics maps that we've seen here. So E goes to 3, X goes to 9, and so on. The maps are, as you know, unordered, so these letters, these bindings will appear in any order that's convenient for the implementation to be stored. Good. So that was step 1. Step 2 is I want to map not just a single character, but a whole word to the digit string it can represent. So for instance, the word Java should map to 5282 because J maps to 5, A maps to 2, and so on. So how can I achieve that? Well, that's a simple map, right? I want to apply the same operation on every character in the word. So what I would write here, I would say word map car code. And that makes use of the fact that in fact maps, like car codes, are functions themselves. You've seen that before, so we can use a map as the function of a map method. Okay. So we have word code. Let's test it. Word code of Java. That gives us indeed 5282. But that was all uppercase. If we apply it to a lowercase character, oops, we get a no such element exception, key not found. And the key that wasn't found was the lowercase a. Well, that's pretty understandable because, after all, our map went only from uppercase characters to digits, not from lowercase characters. So the best way to correct it would be to simply convert the word to uppercase using Java method on string to uppercase, and that will do the trick. So now Java would map to 5282 as we expect. Good. The next step then would be to go again the other way. So we know that Java maps to 5282. What I want now is a list of all the words that map to 5282. So I want to go the other way. I want to go from 5282 and I want to find all the words that map to it. And the same, of course, for every digit string. So I will call this another map called words for num. And that then would be a map from strings, namely digit strings, to a sequence of strings. So that's the sequence of all the possible words that I have in this list. So how do I do that? Well, if you think about it, then really what we want to do is a group by. We want to group lists of words that have the same code. And we want to then, given the code, retrieve that list. So it's simply a words group by. And the function we use as the discriminator function is word code. So here's a small glitch. The error message here says that the group by is not a member of the type iterator of string, which is a type of words. And that's true. The problem here is that words is an iterator, which is the same as a Java iterator, and it doesn't have a group by method. We haven't really covered iterators in this course because it's an imperative concept. So the best way to fix the problem here is to just convert the iterator to a list, and we can do that with the toList method. So now words is a list, and if we print it, then we see first the output that we see the word list. So that looks like the prefix of a dictionary until the output exceeds the cutoff limit. By the way, if you use the first version of the worksheet, then you will have gotten the same thing, that the output exceeds the cutoff limit, but then you wouldn't get any further output because there was a problem that the cutoff limit was determined for the whole worksheet rather than for each command separately. If you see that problem, then you should update your worksheet, and that will take care of it. So let's see what the worksheet gives us. Otherwise, we see here a no such element exception that a key was not found, and the key not found was a minus. Let's try to track that down. What we see here, we see a stack of methods that all came from the collection hierarchies. And then the first method that we wrote was word code itself. So it seems that in word code, we pass a key to car code that wasn't found. And the key here was a minus. Car code, of course, takes care only of uppercase letters, whereas minus is not a letter at all. So it seems the diagnosis is that our dictionary contains words that contain an embedded hyphen, and our code here can't deal with those. So I propose the best way to deal with that is simply to drop words containing hyphens or other non-letter characters from our word list. So let's try to do that. So we say we have a word list and we want to retain all the words that only consist of letters. So retain would be a filter, and we would then say word for all, so all characters for the word are a letter. And if we do that, then we still get the same dictionary, but scrolling down, actually words for num now gives us a true map that has as a prefix the things that you see here. Okay, great. So almost the final thing to do now is to write function encode. And function encode would return all ways to encode a number given as a digit string as a list of words. So it would give us a set of list of strings, that's the words in each phrase, and the set contains all the possible solutions. So far all our implementations of methods were some simple application of a method that's defined in the Scala collection libraries. With encode we're not so lucky, so there's nothing directly that represents encode, so we have to work on it ourselves. A good strategy here is, if you're given data like a string or a list or something, to always take care of the boundary cases first. So the boundary case here would be, what do you do if the number is empty? What should you return then? The empty set? Well, the answer is no, not really, because the empty number does have a solution, and it's the empty phrase. The empty phrase represents the empty number, and the empty phrase would be just represented as an empty list. So I argue that should be the right result for empty numbers. Okay, so if the number is not empty, what do we do? Well, the new thing here is we're dealing with phrases instead of words. So we need to determine essentially how many characters we take from this number to form the first word. And here we have a choice. That number could range from 1 to the length of the number itself. So we could say for split taken from 1 to number.length. So that's where we want to split our number, and up to the characters up to the split would form the first word, and the rest would form the other words. So let's see how we go on then. So once we have a split, we can find out what the first word should be. So that word would come in words for num of the number with the first split characters taken. So we take the first split characters from the number, we apply words for num, so that gives us a sequence of all the strings that have this number, and we let word range over that. Good, almost done. The other thing we need to do is to say, well, once we have taken split characters of the number, we need to treat the rest of the number. So what we need to do is we need to do something with the number drop split. That's the rest of the number. And what do we need to do? Well, we apply encode to it. And so once we have that, we can compose our solution. The solution would consist of the first word followed by the rest. So we get an error here. The error message says that there's a type error. It found an index sequence and it required a set. Index sequence, you remember, we got that because we started with a range, and of course the result can't be represented as a range, so the Scala type inferencer will widen the type, and the next available one is index sequence, which has vector as its primary implementation. So that's of course incompatible with a set, so we have to convert the whole thing to a set, and the one way to do that, we could do that at the end, simply write toSet for the result here. And that would give us a valid encode method. So let's test encode. I have prepared a test case here with a digit string. Let's see what that gives. We get a no such element exception, key not found 7. So it seems we're not done yet. What happened here? Well, if we look at where the key wasn't found, it was in the encode function itself. So the map that we apply here is words for num. So obviously we have a key where that is not contained in the words for num map. That was the key was the string 7. And that becomes clear if you look at the mnemonics map. So 7 maps to PQRS, and indeed there's no single letter word that consists of any of these 4 letters. So how can we fix that? Well, you have seen in a previous session that one way to deal with these key not found errors is to make your maps total. And we can do that for words for num. We can make the map total by adding a default. So we say with default value. And what should be the default value be? Well, we have a map to a sequence of all possible solutions, so I guess the empty sequence is a good default value. So essentially if a key is not in the map, then we say, well, it doesn't have a word that's associated with that digit string. So if we do that, then indeed we do get a result, and we get a number of phrases. The one we're after is this one here. Scala is fun is one of the possible solutions, so that's what we wanted here. You can play with other possible numbers and see what they give. Good. So one more thing to do. We got the solutions as a set of lists, but what I really would like to do is present them as complete phrases. So what I want to do is I want to write a method translate that gets a number and returns a set of, not list of strings, but strings, where the string should be the whole phrase. So how do we do that? Well, we start with encode number, and then for each solution, which is a list of strings, we have to present this list solution as a phrase. So for each means we have a map, and the operation we want to apply is a make string operation where we separate the words in the list with spaces. So let's see what that gives. If we now do translate of the digit string here, then indeed we get all the solutions as phrases, and one of them was the one we're after. So that's it. I hope you have gotten an impression how much fun it is to write programs in an interactive way using immutable data structures and functions only. In fact, I think that the immutable collections that you see in Scala and a couple other languages are something that will play an increasingly important role for the future of programming in general. They're just too good not to have them. They're very easy to use because generally a few steps are sufficient to do the job. They're very concise. Typically one word replaces a whole loop. They're safe. So the type checker that you've seen is really good at catching the errors. Typical errors we had when we wrote the program were key not found errors. That's true. That's one thing the type checker doesn't check. But a lot of the other annoying errors are already caught during compile time. You don't need to test your program to find them. The immutable collections are also pretty fast because the collection operations are tuned in the library, and it turns out they can also be parallelized. And finally, they're universal. There's one vocabulary that works on all kinds of collections, from lists to vectors to ranges to sequences to sets to maps, but also to further kind of collections like parallel collections or even distributed collections that you would typically attack with MapReduce jobs. And I believe that makes them a really very attractive tool for software development.